we look at a class of problem in finding extreme values when we have points on a circle. In this particular case, the circle is centered at 3, 0, radius 2. We try to find mean, max of these three quantities. Of course, today we're going to introduce a new method, that is to use Cauchy Schwarz Inequality in solving these sort of problems. Let's get started. Now, when you see these problems, you're going to always start with geometric interpretation of the problem. Now here, the points are on the blue circle. Now the quantity we try to minimize is y over x. What is that? That is the slope of the red lines here, right? So as we move the straight line is actually from the origin 0, 0 to the points on the circle. Of course, the mean or max is always achieved when this straight line here is tangent to the circle, right? Of course, the slope of tangent with this particular circle is given by this, x minus 3 over negative y, right? And with that, and also that you have to satisfy the equation of the circle. In this case, we're going to rewrite the equation like this. So you solve these two problems, and then you find the extreme value, right? So in this case, I'm going to skip the details. This is achieved when x equals 5 over 3, and the value here, of course, we try to minimize, so we're going to take the negative value here, is negative 2 square root of 2 over 5. That's the solution. Okay, that's good. Now, the second problem, we try to max y minus x. What is that? Notice that y minus x equal constant representing the straight line here marked in red. Okay, so again, this happens when the straight line touches the circle as a tangent point, right? So that is where the max and the mean is achieved. Okay, so from this graph, you know that the max value is when we move the top straight line a little bit down. So in other words, the max value is the negative value here, right? That's just a geometric intuition, which is always important in understanding these sort of problems. Again, the extreme value happens when we have tangent line, right? So here, tangent line, the scope is going to be 1, right? Y minus x equal, this kind of line of, these lines always have slope 1, right? So if you plug in, you can solve, the value here. Again, I skip some of the details. The extreme value is achieved when x, y equals these values, and the actual value is 2 square root of 2 minus 3. That is a negative value, right? Okay, the third case, we try to maximize x squared plus y squared. What is that? Now, again, the circles in red, that's representing x squared plus y squared equals certain values. And again, here, the extreme value happens when the two circles, the red and the blue, touch each other, right? When, in this diagram, we have shown the minimum case, but of course, we try to find the maximum case, right? So in this case, again, once you have the interpretation, it's kind of easy to solve. You plug in here, you notice that, the C, the constant we're looking for, is satisfied in this range, right? And then the extreme value is 1 and 25. In this case, we're looking for the max value, so that max is 25. All right, that's good. So this is just, it's good always to have the geometric understanding of the problem, all right? But of course, usually there is another very common way of solving this problem, that is to use parametric equation of a circle, right? So we're dealing with points on a circle, Now, you know that the parametric equation for the points, in our case, the center of the circle is 3, 0, the radius r, so the parametric representation is going to be x equals 3 plus 2 cosine theta, and y equal to sine theta. Here, theta is the parameter, right? So now, you want to find the extreme values of the three quantities, right? Let's represent that in terms of theta, a function of theta, right? Let's do that. So, here we have f1, f2, f3. Now, the problem is a mean or max problem of a function in theta, okay? So, you're going to take the derivative, find the extreme values, and then you get the answer. Again, I skip the details. That's not the focus of today, but it's good to know, this a common method is to use parametric equations for the points on the circle, right? So we have the answer here by minimizing this function in theta, right? And this is again the maximizing f2, right? And max up that. All right, so that's again very common. You should know how to do this using the parametric equations. All right. All right. So here is the main topic today, which is Cauchy Schwarz Inequality. It's very useful and powerful tool. It allows us to solve a lot of problems in finding mean or max values. Okay, so what it says is that if you have two sequence numbers ai and b sub i's, then the sum of square of ai times sum square of bi is always greater or equal to the inner product type of thing square, right? So as a matter of fact, if you learn vector algebra, there's another term of inequality in that form. All right. Of course, you may ask when the equality holds. The equality happens either one of the sequence is 0, like a sub I all 0 or b sub I all zeros, right? Or the ai over bi is a constant value. All right, so in the vector case, it's gonna be this, right? What it says is that the inner product, right, of two vectors, and the magnitude of that, right, is always smaller than the length product. Right, the length of u and the length of v, right? So that's also very useful, in interpretation of the Cauchy Schwarz inequality. All right. So of course, a special case would be I only have two pairs of numbers a, b, c, d as real numbers. Then we're gonna have this inequality. It's very useful in solving a lot of like high school math problems. All right, so here of course let's start with one example, right? Let's look at this problem. So we have points xyz in 3D, and to satisfy this equation, of course we know that this representing the points on this plane. We'll try to minimize x squared plus y squared plus z squared. What is that? That is the square of the distance from the the origin with 0, 0, 0 to the points, right? Of course, if you learn calculus, you know that the answer to this would be square of the distance from the origin, which is 0, 0, 0 to this plane, right? There's a formula you can plug in, and then that would be the answer. But here we're going to use Cauchy Schwarz inequality, right? Now here's the inequality, right? Given by Cauchy Schwarz inequality that we just learned earlier. Now the magic here is actually try to figure out what is AI, what is BI. Of course, in this case, AI is XYZ, the BI is 1, 2, 3. But how do we figure that out? Okay, so it's really related to the condition we're given, right? Because we're given x times 1, y times 2, z times 3, right? It's kind of an inner product. So here you choose 1, 2, 3 as the other sequence, right? So you plug in the numbers because we're given that x plus 2y plus 3z is a constant, so that the square is going to be 49. Of course, this is actually 14. So what you get is that x squared, y squared, z squared is going to be bounded by 49 over 14, and that is 7 over 2. Okay, that's the answer. Okay, so you're going to use these to solve other minimization problem like this. Okay, so the key here is finding the right coefficient here, the b sub i's, okay? All right, so now let's go back to our original problem. Original problem is try to find mean or max of those quantities for all the points on this circle. Now this time we're going to use Cauchy Schwarz inequality. So this is method number 3, right? So let's look at this. All right, so how do we use Cauchy Schwarz? Again, it's important to figure out what is the b sub i's, those coefficients, right? So let's think about it. So let's assume y of x equals c constant, right? We try to minimize this constant c here, all right? Now here is the magic, okay? So the coefficient here we chose is actually c and -1, right? Of course, we know that the points on the circle satisfies, that is quantity 4 here, and then we have this inequality. Then if you rearrange it, you know that c² is bounded above by 4 for 5. Of course, the minimum value would be this one, right? So again, the key here is find out what coefficient to use, right? So here we chose c-1 as coefficient. Why? Because that's related to the fact that we want to minimize this quantity, and this quantity has y over x equals c. In other words, y equals cx. So that's how you chose a coefficient. Now y minus x, again, what coefficient to choose? Okay, here is the key. Now in this case, again, we're going to assume that is constant c, and then we try to max c here, right? So, and the Cauchy Schwarz is this one, okay? The coefficient we chose is -1, okay? So because we have y minus x, right? We want to construct y minus x to the right hand side, right? That's why we choose -1 for the x, and we choose 1 for the y, right? And then when again you plug in the constant here, right? Because the quantity over there, the first quantity is actually 4. So you plug in here, this is your equation, right? And from there, you know that the max c is achieved with this, okay? So now you know the trick, okay? So the third one, again, this is a constant c. You plug in here, you figured out that c would equal cx minus 5. So how are we gonna have that? Y is gone, okay? So in this case, the coefficient for y is gonna be 0. Coefficient for x is gonna be 6. So let's do that. So we chose 6 and 0, right? So we plug in, we have this inequality here, plug in the constant, and then we know the range for c is between 1 and 25. All right, so that's it. So notice that go back and review, why we come up with this coefficient. It's really we're gonna look at the constant, bi's, so that when we have the cross product, it will have something that we know, either the condition or some target values. All right, so you can practice with some similar problems. Sometimes a variant of the problem would be the points on a maybe eclipse, or on some equations, not necessarily on the circle, could be on 3D, would be on a sphere, things like that. You can always use Cauchy Schwarz as an approach to solving the problems. All right, thank you for your time.